now we say that we got the law for a closed system. What will be the expression of the first law for a control volume? So first law for a control volume. The logic we will do is very similar to what we did for conservation of mass. At the end of that, but what instead of looking at mass, we will look at energy. Okay. So before I think there's a question there. Let's see what it is. Does an isolated system have zero work done or not? And why? Okay. Okay, isolated system means it has absolutely no interactions with the surroundings whatsoever. So work will be zero. Heat will also be zero. Okay. Okay, first law. And now for a control volume. So let's go back to that picture that we made for control the mass. This is what we made. The thing is, we will apply the same sort of arguments, but this time look at energy. And at the end of that, we will come up with a long expression. And that's one of the longest expressions you will come across in this course, but it is the most important one for many, many types of problems. But fortunately, we can simplify it in many cases and get a very compact expression from which we can solve problems. That part we will do when we look at specific problems, not right now. Right now we will say, look, doesn't matter what the application is, what the working substance is, what is the law, first law statement for a control volume. Okay, so here is how we do it. We do the same thing here. And now we need to talk about, instead of looking at mass of the control volume at T1 and T2, we will look at energy of the control volume at T1. That means whatever substance was there, what was its energy at time T1 and what was the energy at time T2. So the energy at time T2 here we'll say was ECV at time T2. And during this process, we say that there was delta Q CV heat transferred to the system, so it will be a plus, and delta W CV work done by the system on the surroundings. So we are keeping both with a plus sign. So I'm not showing it on this diagram or this diagram because both are transitory at the system boundary and they occur over the duration of the process. So that's the additional thing that has come in. We define the energy of this. Now we say, well, what was the energy of the control mass at time T1? We looked at mass of the control mass at time T1. Now we say my control mass is this whole thing plus this little thing. What is the energy of this control mass? And we will equate that with the energy of this control mass plus all these other things that are coming in. So we'll write some expressions now. I'll keep this here so you can see that. So that energy of the control mass at time T1 is equal to energy in the control volume, which is ECV at T1 plus energy of this little thing, which is delta Mi times its specific energy. I haven't said this, but specific energy E, like U, is nothing but E upon M. Like we said, small u is U upon M. Okay, so specific energy. What it has is all three terms, U, kinetic energy and potential energy, all are there in this. Energy of the control volume, well, whatever substance was there, then again the same thing, its internal energy U plus its potential energy plus its kinetic energy. But that applied to the control volume. In this case, we are applying this to this little mass. At time T2, the same story, that our mass, that little element has gone in, but some element has come out. This is ECV at T2 plus delta ME, what exited, multiplied by its specific energy. So Now we say, I'm going to apply this equation for a control mass. What is the equation that I have to finally use? So for us, that equation is Q12 is equal to W12 plus E2 minus E1. So we want to put some terms into this that are relevant to the control volume. Q12 is in the process, what are the energy transferred because of temperature difference, and that we have already said is delta Q CV. So this term becomes delta Q CV. This work term has two parts. One part is the work done on the system boundary, which is delta work CV, and the two terms which were related to work associated with this fluid going in and this fluid coming out. So this going in, if you remember in the earlier discussion, this was minus PI VI, and this term was plus PE VE. We defined this as the flow work, something being pushed in, work done on the system, minus PI VI, work done by the system in pushing the element out, PE VE. Okay, so now E2 minus E1, well here it is, this is E2, this is E1, and now we'll put all these terms into this equation. So we start getting a longish type of an equation, and we start putting some things more down. We will substitute the small e by u plus v square by 2 plus gz with the appropriate subscripts, I for the inlet, E for the exit. And let's now work on this big equation. What we get, the left side is delta QCV. This is equal to minus PIVI plus PEVE plus delta WCV. They are all our work terms. And the energy terms, this minus this, so we'll first take these two terms, put them together. That becomes ECV at T2 minus ECV at T1 plus delta ME EE minus delta MI PI. What we will do next is a little combination. We see this PI VI coming here and this thing coming here. And on this side, we have this and this. So we'll combine these. And that gives us this delta WCV stays plus this term for the control volume. I'll just skip that, plus this into delta MI, if I remember right. I was missing a term there. This is this into delta MI into delta ME. So we get delta ME EE plus PEVE plus delta MI, sorry, minus here now, EI plus PI VI. Now we open up this term and we'll do a little simplification on this. So we say that, say EE plus PEVE is equal to UE plus VE square by 2 plus GZE plus PEV. And this gives us the same combination again, UE plus PEVE plus VE square by 2 plus GZE. And this we have just defined, this combination of properties, HE plus VE square by 2 plus GZE. Similarly, we can do for the inflow term and then go back to writing this long equation once again. That tells us that delta Q CV is equal to delta W CV plus, what I'll do now is for this little term, we will say that this is delta E of CV, and then we got these two terms coming in here, plus delta ME into HE plus VE square by 2 plus GZE minus delta MI HI plus VI square by 2 plus GZI. And this is the same two steps as earlier now, divide by delta T and let delta T go to 0. And when you do that, this is heat transfer in a little time interval divided by the time. This is rate of heat transfer into the control volume, which we will call Q dot CV. So this is the rate at which heat is transferred to the system due to a temperature difference. This is equal to work rate of the system plus rate of change of energy of the control volume plus this first term, which is delta ME over delta T, like before, becomes M dot E, but inside we have HE plus VE square by 2 plus GZE minus M dot I HI plus VI square by 2 plus GZI. So this is the energy, including the flow work associated with each mass flow into the system, exiting of the system, and minus inflows. If there are more than one inflows, more than one outflows, we will generalize this equation and put that this is summation for every mass outflow, summation of every mass inflow, and this becomes our equation for the first law for a control volume. The only thing left there was that what was this ECV? This is UCV plus half MCV V square by V square plus MCV GZ CV. So in this expression, if we get the mass out, it will become specific internal energy of the control volume plus its kinetic energy, half V square plus GZ. This is remaining as an internal energy term, whereas on the flow terms, this became a specific enthalpy. We have to keep that in mind, that the control volume, its energy remains as U, whereas the flow terms got HI because they included the internal energy of the substance and the flow work associated with that. So that's why this is H here. And so in any problem where you have a flow rate, we promptly will get down to H. Okay, so that's a big long equation which we will have to again remember all the time. You can rearrange the term by saying that this is inflow. You can get this term to the right side and say that's also an inflow. So if you want to recast this equation, this becomes Q dot CV plus summation of all inflows m dot I hi plus vi square by 2 plus gzi. This is equal to d dt mass of the control volume uCV plus vCV square by 2 plus gzCV plus outflow m dot E he plus ve square by 2 plus gze plus w dot c. That's your complete equation. I have substituted everything now in this. Nothing is left for guessing now. And what this equation tells you is that this is energy inflow rate, energy outflow rate, rate of storage of energy in the control volume is equal to rate of creation of energy, which is 0. Okay, so this is our most general form of the first law of thermodynamics for a control volume. The solution of every problem should begin from here and preceded by the conservation of mass, which was the other equation that we got. So those are the two equations which get us going in solving any problem. So at the time we have, we'll take questions, and also if there be a few examples I will take. Okay, let's look at an example and take a, we have to take a flow system. So we'll take a, say a pipe through which something is flowing over this portion, and here it is, say, being heated. You know, this is what happens inside the evaporator of an air conditioner. So how can I analyze this? And first thing we say, okay, let us see what is the application. The application is a tube. Over a certain portion there is heat transfer taking place. For the other portions there is no heat transfer taking place. The next thing we do is define the system boundary, which is this. And so now I will write the conservation of mass for this and conservation of energy for this. So the first thing to do is define the state points. This is 1, this is 2. You can also call this inlet I and exit E. That's okay. As long as there is only one inlet, one exit, this works. More than one, it doesn't work. And we take the conservation of mass. And that full equation that we had there, I'll just put it up for display. Yes, this is what we had. M dot E minus M dot I summation plus d dt mCV equal to 0. For this case, this will become M dot 2 minus M dot 1 plus d dt mCV equal to 0. And we now write that huge long equation and say what is the conservation of energy, or the first law. We already said that this is an open system, so we will use the control volume approach, so that is why we use this equation. Conservation of energy tells us all this. QCV, yes, there is some heating taking place, so this QCV exists. There is one inflow, so we have Q dot CV plus M dot 1 into H1 plus V1 square by 2 plus GZ1. This is equal to the energy of the control volume, which we will just put for the time being as ddt of something. There is no work transfer, you can see here, and this work is system boundary work and not flow work. So we are quite happy to say that there is no work transfer in the system, so W dot CV is 0, and the only term left on the other side is m dot 2 h2 plus v2 square by 2 plus gz2. Okay. And now we say, well, what else can I do to make life simple? And so I'll assume that this system is in steady state. That helps us in that this term will disappear, this term will disappear. And if this term disappears, the conservation of mass equation tells us m dot 1 is equal to m dot 2, and this will say, well, whatever it was, 5 kg per second, 1 kg per second, whatever, now you can put a generic thing as m dot. And then we come to this equation and say, well, this is a tube, this is a horizontal tube, so I'm quite okay to say that Z1 is equal to Z2 because it's a horizontal tube. And if I know nothing about the velocity of this, I'll say velocities are very much comparable. So V1 is of the order of V2. And so with this m dot 1 gz1 and m dot 2 gz2, these two terms will disappear. And these two velocity terms are of comparable magnitude. This is something we could check later on or see the application and see what happens. So this and this will go. And in the end, what we are left is q dot cv on this side plus m dot 1 h1 is equal to m dot 2 h2, or heat transfer rate is equal to m dot into h2 minus h1. So you've got a very, very nice, simple, compact equation coming up here. From here we can get the properties. If I know state at 2, we can get H2. State at 1 is to be needed. So for H2, I need two independent properties at state 2. For H1, we need two independent at state 1. M dot needs to be given. If these are given, then Q dot CV can be calculated. So that's an illustration of how we proceed in solving problems which are of a flow type of a system where we need to calculate energy and work transfer. There are many more such applications that we will look at. This is an example of what one may call heat transfer or a heat exchanger. There will be many more things coming up like turbines and compressors. And then instead of a flow, if we had a reciprocating system like one example we took, that will not have these equations but have those equations for a control mass. Okay, so there's some more questions here. Yeah. Why are we not talking small d instead of del in the expression of the first law? Okay. Okay, this is a thing coming up again. Okay, I don't have it. The question is this. I wrote the first law as delta Q is equal to delta W plus dE. And the question is, why are we using delta and not d? What's wrong if I write the equation of the first law as dq is equal to dw plus de? This is the question, and the answer is heat and work are not properties of a substance. They depend on the path, which means that they are inexact differentials. dq means this is an exact differential, and I can say that heat is q2 minus q1 by integrating it. But we don't define q for a system. That's another way of looking at it, that q of a system is not defined. Our definition of heat is that form of energy which crosses a system boundary due to a temperature difference. A system does not contain heat. And similarly, work is work done at the system boundary which has the sole effect of lifting a weight or which is forced into a distance. So there are two good reasons why we cannot write dq, and this is wrong and this is also wrong, and that's why we have the equation in this way. Energy, though, is a property of the system. It does not depend how the system got there, and that's why we are justified in writing this as dE. And when we integrate it from 1 to 2, this we can write as E2 minus 1. And the same thing is integral of du, why u is also a property. This can be written as u2 minus u1, and same thing with your potential energy and kinetic energy. That's why we got the terms here. Potential energy was mg z2 minus z1, and this was half m v2 square minus v1 square. So these are properties, and you can physically, if you want to see it, you can see these two, that if you lifted a weight from this height to this height, whether you just lifted it straight or whether you lifted it high up and then brought it down, or whether you lifted it up and then went up like this and then came here, the change in energy is always going to be the same. It's not dependent on these are the paths. This is path 1, this is path 2, this is path 3. It doesn't depend on the path. It's only the initial and final points where it depends on. So that's why kinetic energy, potential energy, and internal energy, all these are point functions, and so exact differentials. Okay, another one, it says, can we say dW is equal to U2 minus U1 in an isolated system? What is the other question? We have taken 3D control volume, so there should be partial derivative in all equations. Which equations? No, okay, so let's take this one. The question is, because the 3D system, why are we taking d dt as this and not as a partial derivative? Well, it is, they have said that everything in the system is included in the mass. So the dimensional dependence is gone. So you don't need to worry about that. We are only saying whatever is the total mass in the system, what is it that we are looking at. And we are saying that MCV does not depend on anything else either. So, but if you want to express this in terms of volume and space coordinates, then you are right. The space coordinates will come here. Those will be partial differentials in space, x, y, z. Yes. Okay, so that's the reason for that. Okay, the question, isolated system, zero work done or not? Okay, that's been answered. Okay, can we say dW equal to U2 minus U1? Well, this will be the case, not when it is an isolated system. Isolated system means it has no interactions with the surroundings. So Q12 is 0, W12 is 0. So U2 will be U1, nothing will change. Anyway, dW writing is wrong. The correct word should have been W12 or integral dW1 to 2. If this has to be equal to U2 minus U1, it means that delta Q should be 0, or integral delta Q1 to 2 should be 0, which implies that the system should be adiabatic. Adiabatic system means it has no heat transfer with surroundings. Okay, that is the case under which this will be true. Adiabatic system, not an isolated system. Okay, so what we have learnt is, we came across some new concepts today. Let me just summarize and then we will quit for now. We got the idea of what is a mass flow rate and the idea of a flow work. Then we derived the first law statement for a cycle and then for a process, and during that we came across a new property which is energy and a new property internal energy, and then we applied this first law, got a long equation for a control volume. So we have now all the two of the most important things in doing all types of problems, which is this and this. What we'll do in tomorrow's lecture is to look at a few more examples and applications before we move on to the second law of thermodynamics. So, thank you.